Mr. Wilcox spends a full day at Gingerman Raceway testing some new tires on his Honda Civic. For 400 laps, he records his lap time in minutes at the end of the day. He plots the distribution of times and realizes that it follows an approximately normal distribution with a mean of 1.84 and a standard deviation of 0.07. So you should have worked through this all by hand, and I'm going to show you how you could use a calculator to do this and further problems. So Mr. Wilcox would like his lap times to be consistently between 1.75 and 1.85 minutes. What proportion of his laps are in this range? Interpret your results in context of the problem. So you should have once again done this by hand, have your interpretation already. So I'm just going to help you out with how could we use our calculator to make this a lot easier. So we have our normal distribution, there's our mean. We're looking at from 1.75 to 1.85. So this is that area that we're trying to find, and you should already have an answer to that. But now how could we do this on our calculator? So our calculator actually has a formula that is called a normal CDF, and that stands for cumulative distribution function. So how we use this is we find our lower bound, our upper, our mean, and our standard deviation, and we can all plug this all just into this formula that our calculator has. So it's really doing like the z-scores and the table A work for us. So in this case, in our calculator, we would plug in normal CDF, and we would press 1.75 for our lower, comma 1.84 or 85 for our upper, comma 1.84 for our mean, and 0.07 for our standard deviation. So you can totally use this on a free response. If you are, you have to make sure you include both of these parts. This is telling the grader that you understand what is happening when you are plugging these in. You know that what your lower bound is, your upper, your mean, and standard deviation. So now how do we plug these in? It's actually two pretty quick steps, kind of three. So first you're gonna press shift and then vars. So because above that is distribution. I'm sorry, it's not shift, it's second. So second vars, and this gives us our distribution tab. After you press that, you're going to press 2 for normal CDF, or you can just scroll down to 2, enter, and then we can just type in those. So we have our lower was 1.75, enter, our upper 1.85, enter, our mean, I already have it typed in there, 1.84, standard deviation 0.07, and paste and enter, and we should have roughly the same thing that you got from using table A. So it should be about 45.75%. It might be off by a decimal or two, but it should be pretty close. So that is how we use our calculator. So number 2, in order to beat Tom, Mr. Wilcox needs to have lap times that are less than 1.72 minutes. Find the proportion of laps that were faster than 1.72 minutes. So when we look at our curve, here's our standard deviation. 1.72 is less than that, and we want to find our lap times that are below that. So you might be like, but we only have one bound. That is true. So we need to think of a really small number that we could put in. So once again, you need on a free response, normal CDF, lower, upper, mean, and standard deviation in order to get points for using this. So normal, our really small number that we're going to use is negative 9,999. That'll help us get to the most accurate number. And then our upper bound is that 1.72. And then our mean is still that 1.84. And our standard deviation is still that 0.07. So then we repeat the process. Second distribution, normal CDF, and we change our numbers. Our lower is negative 9,999. Our upper is that 1.72. Our mean's the same, standard deviation's the same, and oh, I pressed a minus instead of a negative. So the negative's at that bottom. And we get approximately 4.32%. So for your context, 4.32% of the laps are less than 1.72 minutes, or 1.72 minutes or less. All right, number 3. So I'm gonna pause the video, set it up, and I want you to try and do the same. All right, so for this, we were looking at everything that's more than 2 minutes. So similar idea to the last one, except it's everything above 2 minutes. So 2 is our lower bound, and for our upper bound, we need a really large number. So we'll use a positive 9,999. Same mean and same standard deviation. Enter. And that is approximately 1.11%. So in context, 1.11% of the lap times are more than 2 minutes. And then this last one's a little different. We have what lap time is necessary. So this time we want to find our lap time for Mr. Wilcox to be in the fastest 3% of all his laps. Interpret your results in context of the problem. So these are like those last couple we saw in yesterday's lesson, where we know that area is 3%, which as a decimal is 0.003. Sorry, scratch that. As a decimal, it's 0.03. And we want to find that lap time. So our calculator actually has a function for that as well. It's like we're working backwards, so we want to think of it as doing the inverse. So this is called the inverse norm. So for our inverse norm, you use your percentage, and then your mean and standard deviation. And I actually just realized I drew my picture wrong. So if he's in the fastest 3%, it would be shaded on the other end. So this would be that shaded. So for our percentage, we put it in as a decimal, so that 0.03. We're still working with that same mean. And then our standard deviation is still that 0.07. So this is similar to your table A, where it will always show everything below. So if we did want anything above, we'd have to do that subtraction. But since we have below, we go to second distribution, and we see 3 is that inverse normal. So our area is that percentage, or as the decimal 0.03, our standard deviation, our mean, and then our standard deviation. Enter, enter, and so this lap time he needs is 1.71 minutes. So the context, to be in the fastest 3% of all his laps, Mr. Wilcox needs a lap time of 1.71 minutes. So this is just another way for you to solve these problems. If you would rather continue using table A, you totally can, but this is a lot quicker of a calculation.